Yeah, I think probably maybe the fastest way to do this is, well, balancing it. You got to balance it. It came out to 1 to 5 to 3 to 4 mole ratio. I think most people got that. But Avogadro's law says that the mole ratio can also be the volume ratio as long as we're at constant pressure. The temperature should be the same. Since we're at constant pressure, you know, all the gases are at 1 atmosphere, then we can say we're going to have a 1 liter, 5 liter, 3 liter, 4 liter ratio. And so you could do this instead. Instead of going from liters to moles, and then moles to moles, and then moles to liters, we can go straight from liters to liters here. So some people did this. And you need to show, this is a limiting reagent problem because I'm giving you both reagents. So in the limiting reagent problem, we're going to use a smaller amount method. And the smaller amount of CO2 is this. And that means that after 127 liters of O2 is completely consumed, we're only going to make 76 liters of CO2. There's no way we can get 93 liters because we don't have enough oxygen. It's going to consume all the oxygen. In fact, I didn't ask you this, but how much of the propane is consumed? And so how much C3H8 is consumed? Well, not all of it, because the oxygen, this is called our limiting reagent, our LR, and the 31 liters of propane, this is our excess reagent. And so the excess reagent, we're going to have some left over. Well, we can figure out how much is consumed by the LR. So if we have 127 liters of O2, that's going to completely react, and then that's going to consume how much? Well, for every 1 liter of propane, we require 5 liters of O2. So this 127 divided by 5. Is 25.4 liters of propane consumed. What some people do is they say the total amount of CO2 is 93 plus 76. Is that correct? No, it isn't, because once we make 76, there's no more O2 left. And then once we've consumed all 127 liters of O2, we've only consumed 25.4 liters of the propane, which means there's going to be about 6.6 liters of, is that right? 6, no, not 6.6, 5.6. There's going to be 5.6 or about 6 liters of propane unreacted. In other words, it's going to be 31 liters minus the amount consumed. That gives you the amount remaining unreacted. And so about 6 liters of propane remain. But this was the answer I was looking for. How many sig figs are we allowed in this one? 2. Well, it looks like 3. So we'll just go 76.2 liters of CO2. Well, the propane's in excess. And so you don't really need to worry about that. We're not going to use all of it. You could, I mean, 2 sig figs, that's okay as well. Here, let's see. All right, so is that clear for this? This is the way I would have done it. Or you could have used the molar volume. You know, the molar volume is quick. What's the molar volume at RT in 1 atmosphere? Yeah, 24.5 liters per mole. That's good also. Or you could use ideal gas law. You can go from liters to moles, you know, because the number of moles is equal to PV over RT.
Could you use ATM?
Well, we could, but the tricky thing here is this. If we did this by Dalton's law, How many ATMs of C3H8 do I have? One ATM. How many ATM of O2 do I have? One ATM. CO2? One ATM. And, well, there's something weird. Is there something wrong with my Avogadro's law?
Yes, for gases.
It's for gases. So, is there something weird? Did I make a mistake? Yeah, I made a mistake. What was my mistake? 4 liters of H2O. Is that right? No, that's wrong. This is impossible here. It's impossible because it's not a gas. H2O is a liquid. So this is the reason. So I'm going to stop here with this. All right. And so the way we do this is this. If I take 1 liter of propane plus 5 liters of O2 plus 3 liters of CO2, how many liters total mixture do I have, let's say? Well, actually, if I take 1 liter, 5 liters, here I'm going to get 6 liters. It's a bit tricky because this is the excess reagent, limiting reagent. So it kind of adds up. But if I do it in terms of atmospheres, then I could do the same thing. I'd have 1 atmosphere of propane, 5 atmospheres of O2, 3 atmospheres of CO2, and water is not a gas. But the difference here is the volume. I'd have to do this in 1 single container. And that 1 single container will start off with a total pressure of 6 atmospheres. Rather than I'd have 2 containers, a 1 liter box and a 5 liter box. When I take a 1 liter box and a 5 liter box to maintain constant pressure, I got to have a 6 liter box at the beginning. So at the beginning, I'm going to have 6 liters. Does that make sense? So I could do it with ATM, but I'm going to have to compress the gas to fill the container. So basically, what it means is this: I'm going to have to inject the propane in here. I'll put in 1 atmosphere of propane, and then I'll put in 5 atmospheres of O2 into this container. And altogether, I'm going to have 6 atmospheres of gas in this container. The pressure is going to be very high. Right? And so what you're doing is you have when you do it with Daltons, you have a fixed volume container and you're injecting the gases in there. When you do it by Avogadro's, you have a box of oxygen and a box of propane, and you put the 2 boxes together to make 1 big box. And so, which one do we use? Well, usually we think in terms of Avogadro's for chemical reactions and stoichiometry because it's easier. When we're dealing with collecting gases over water, then we use Daltons because that's easier to do. So we could do it either way. We could do it atmospheres, or we could do. This is just it's a gas mixture. Propane and oxygen, that's a gas mixture. How do we visualize gas mixtures? We visualize gas mixtures either as an Avogadro's mixture or as a Dalton's mixture. Which one you use depends. In Chem 1A, we have 1 lab experiment in which we do both. We look at it based on a Dalton's mixture, and we look at it based on Avogadro's. So one calculation, we're using Avogadro's, and the very next calculation, we rearrange our thinking and do a 180 in our thinking and do a Dalton's calculation in the same problem. And so that confuses students. They don't really have a clue what's going on, so they just need the equation to punch the numbers in and get an answer. That's it. But I don't think a lot of them don't really understand what's going on.
Does it matter? Oh, I'm pretty sure it matters, but does it matter what type of gas you use with water?
Does it matter what type of gas we do what?
Use with water or oxygen?
What type of gas we use for oxygen? Yeah. Oxygen can come from many different sources. The most common source of oxygen is air. Yeah. And so we use air. But is air 100% oxygen? No, air is about
20% oxygen?
20% oxygen, roughly 20% oxygen. No, we could get 100% oxygen. You just got to pay for it, That's it. Okay, other questions? There was some, like, was it a homework question or what number was it? 45. 45?
Or if you have airdrop,
Okay, well, I can put it up on the screen so everybody can see it. But thanks for that. It shouldn't take long because I remember 45 chapter. Which chapter?
14.
14. So I'll put that up here. All right, chapter 14, number 45. In the natural oxidation of hydrogen sulfide released by decaying organic matter, the following reaction occurs. And so hydrogen sulfide, H2S, and oxygen. So hydrogen sulfide gets oxidized by oxygen, and it gets converted to SO2. What's SO2 called? Well, if it had a charge, like SO3 2- would be sulfite, but this is just sulfur dioxide. Sulfur dioxide gas is poisonous. H2S gas is poisonous too. We have to worry, about generating poisonous gases. So this is why I said, to Francisco, you want to watch out about burning plastics. Because burning plastics can cause some nasty chemicals to be released. In fact, I was looking, maybe I'll just share this right now. I exceeded my article limit. So I was looking at the news. I heard about this thing that happened at Popeye's Chicken. Did you hear about that?
Oh, they got killed, huh?
Yeah. I thought it was due to their chicken sandwich or something like that. But it didn't. It wasn't.
Was it?
Yeah.
What was it about?
Let's see what that was about.
We're trying to cut the line or something. I would have stopped him if he couldn't cut the line.
Yeah. Oh, it wasn't Popeyes. It was Buffalo Wild Wings.
Oh, I saw that and they're coming with those suits.
Yeah. Yeah, you don't want to mix bleach. And the acid was for cleaning scale and lime deposits. So what had happened is bleach is sodium hypochlorite.
Hypochlorite?
Yeah. And they mixed it with some other stuff. It caused a redox reaction, generating chlorine gas. Unfortunately, the chlorine gas is what killed this person. It's pretty sad. The manager, 32-year-old Ryan Baldera, attempted to clean up the liquid and was overcome by fumes. He died later at the hospital. But they had evacuated the restaurants. All the customers left, and it's really too bad. But this happens. People mix bleach with ammonia. Like if you have an ammonia cleaner like this, you don't mix bleach with this. Bleach is an oxidizer, ammonia is a reducer. This is going to generate toxic gases. Yes, yeah, so Windex and
how about chloroxide like Lysol?
Yeah, no good. Don't mix cleaners if you don't know what's going to happen. Well, let's going back to this. You know, H2S. I used to work with H2S all the time, and what I did was I bleached the heck out of H2S. H2S smells like rotten egg, and so I used a lot of bleach, and but I didn't want to generate SO2 because that would be pretty toxic. And so I had the condition so that rather than generating SO2, I generated sulfate. And sulfates aren't that bad. Sulfates don't stink. Sulfates aren't really that toxic. And so I converted all my toxic H2S and H2S derivatives from H2S derivatives are called thiols. And the guy I worked with, he spilled 1 drop of thiol on his brand new tennis shoes. And these were expensive shoes. He's into those really expensive tennis shoes. And he spent weeks trying to clean it. And finally he gave up and threw them away because they smelled so bad. Yeah. But thiols are some of the foulest smelling chemicals on earth. You know, I'm so glad I don't work with thiols anymore. I don't want to go anywhere near it. But if you want to smell what it smells like, go into the Chem 1B lab when they're doing qualitative analysis.
When
they
are they doing that?
They might generate some. I'm not sure. But anyway, this is a rotten egg odor, so you probably easily detect
When I was in
it.
high school, they had this chemical that someone would bring to school every year or so and expose it to the whole school. You had to get out, you had to leave the classroom.
Oh yeah, the spray farts?
Yeah. Yeah, there are lots. What was I watching? I was watching some show, some YouTube, and they put something in a trap. Foul-smelling chemical. Anyway, how many milliliters of hydrogen sulfide measured at 19 degrees C and 549 torr will be used? All right, this is kind of a weird problem, but our book loves this type of problem. Our book loves measuring out the H2S at one temperature and one pressure, and then measuring out the O2 at a different temperature and a different pressure. This is kind of weird, because when you're working in a lab, you usually try to keep things at the same temperature and the same pressure. It's much easier. And so this is why the types of problems in this aren't exactly the ones I like, but there's not much choice here. And so, in this case, we can't really use any shortcuts. And so, the milliliters, how many milliliters measured? Okay, well, we can use one shortcut. And this is it. The one shortcut we could use is that we can go like this. If we have two H2S, and your book loves this type of problem, 3 O2s goes to 2 SO2s plus the 2 H2Os. Now this is critical for H2O. We need to know, is that liquid or is that gas? And then looking at the temperature, it looks like it's got to be a liquid. I mean, if the temperature were over 100 degrees C, then I'd be tempted to put gas down, but it's under 100 degrees C, so I'm going to put H2O liquid here. All right, we know that the mole ratio is the same as the liter ratio. And so this could be 2 liters, this could be 3 liters, this could be 2 liters, and then this is a liquid, so that's not. And so this is the volume ratio for the gases. And so if we use 704 milliliters of O2, if I use 704 milliliters of O2,
Change that to liters.
I could, or I could just do milliliters. I'll just leave it at milliliters. If we have 704 milliliters, that is, what I'm going to do is I'm just going to change these to milliliters. 2 milliliters, 3 milliliters, 2 milliliters. We could use any unit here, 2 gallons, 3 gallons, 2 gallons. It's just going to be a 2:3:2 ratio with whatever units you want. And so if I have 704 milliliters of O2, then how many milliliters of H2S do I need? And so what I can do is I can just do a liter or a volume to volume conversion rather than a mole to mole conversion. So it's going to be 704 milliliters, and then for every 2 milliliters of H2S, I need 3 milliliters of O2. And so we could do it this way. So 704 times 2 divided by 3. 469.3 milliliters of H2S. But the problem is this. It's got to be at the same temperature and pressure. So if we're at the same temperature and pressure, I'm done with the problem. Right? But what they did was they decided to use a different temperature and pressure. Now, since I decided to use a different temperature and pressure, there are 2 ways I can do this. One way is I can do this. This is going to be at 159 torr and 26 degrees C. Your book likes to do it this way. Your book likes to do the combined gas law, so they're going to call this V1, P1, T1. And so what we're going to do is we're going to do a P1, V1 over T1 is equal to a P2, V2 over T2. And then we're going to solve for V2. V2 is going to equal P1 over P2, T2 over T1 times V1. And so P1 is 159 torr, and then we want to go to 549 torr. This is P2. And so 159 over 200, and not 200, 549. 549. The torr cancel. And then T2 over T1. Well, we got to convert this into Kelvin, so this would be 299 Kelvin. And then T2 is 19 degrees C, so that would be 292 Kelvin. So T2 is 292 Kelvin. T1 is 299 Kelvin. And then V1. V1 is 469.3 milliliters. All right, so what does that come out to here? Times 159 divided by 549 times 292 divided by 299. Comes out to 132.7 milliliters of H2S at 19 degrees C and 549 torr. We're allowed 3 sig figs, so change 3 sig figs. So we would get 133 milliliters of H2S. Okay. What the book did was they first converted 704. They converted 704 into the proper temperature and pressure, and then they did the stoichiometry. I did the stoichiometry first and then converted it. It doesn't matter which way you go, you're going to get the same. I probably wouldn't have done it this way. You know which way I would have done it? I probably would have done it this way. I would have just done this as a regular stoichiometry problem and not used the combined gas law. So this is the way I would have done it. Okay, what's your preference, molar volume or ideal gas law? Ideal gas law? Okay. Then the way I would have done this is like this. I would have went from the volume of O2 to the moles of O2 using the ideal gas law. The moles of O2 will equal the pressure of O2 times the volume of O2 divided by RT, the temperature of O2. And so I would have done that. So doing this, what's the pressure of O2? Well, the pressure of O2 is 159 torr. But I don't want torr. What units do I want? ATM. So I'm going to convert it right here in the problem. 1 ATM over 760 torr. And then what's the volume? 704 milliliters, but I don't want milliliters. I want liters. So I'll just go ahead and convert this problem here. The reason I want to do that is because of R. I don't want to memorize different values of R. I only want to memorize one value of R, and that is 0.08206 liters atmosphere per mole Kelvin. So I need to make sure I have the atmospheres as the pressure unit, liters as the volume unit, and Kelvin as the temperature unit. And so the temperature is 26 degrees C, which would be 299 Kelvin here. So when I look at the units here, the atmospheres cancel, the liters cancel, the torr cancel, and the milliliters cancel, the kelvins cancel. Oops, I did this wrong, not there, times up here, 299 Kelvin. Kelvins cancel, and that leaves me with 1 over moles, which is moles. So let's figure out how many moles I've put that to here. So it's 159 divided by 760 times 704 divided by 0.808206 divided by 299. And so I end up with 6.002, some 2 moles of O2. So I end up with 6.002 moles of O2. And then I started with 760 milliliters of O2. All right, so once I have moles of O2, then I'm going to go to moles of H2S using the mole ratio. And so the mole ratio was 2 moles of H2S for every 3 moles of O2. And then I'm going to go from moles of H2S to volume of H2S, or the liters of H2S. And so since you want to use the ideal gas law and not the molar volume, we'll go V is equal to nRT over P. And so in this case, we're going to plug in the moles of H2S into the moles here. And then the temperature, the temperature of the H2S is different. So the temperature of the H2S is 19 degrees C, which would be 292 Kelvin. And the pressure of the H2S is 549 torr, which we would convert to atmosphere. And then we can plug that in up here and then solve for the volume. So this is probably the way I would have done it. Okay, are there any questions on this? Does that answer your question, Lexi, or was it a different question? So the more ways you can solve the problem, the better. The better you'll get at solving these, and the faster you'll get at solving these. So basically, if you want a rundown, were there any other questions before we move on? All right, what did we cover in chapter 15 so far? So Alexis, was it from the beginning? You want a rundown from the beginning? A little review?
talk about dipoles.
We talked about gas mixtures. Your book doesn't talk about Avogadros in this section here, but they talk about Avogadros in other sections, so I just put it both together. We have Dalton's, and we have Avogadro's way of describing the gas mixture. This is Dalton's, 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 Dalton's. Where's Avogadro's? Avogadro's is in another chapter. Dalton's. Sometimes Dalton's is better. So when we collect gases over water, Dalton's is easier because the pressure doesn't depend on the total volume of the container, whereas the volume would. Then we talked about some properties of liquids. Properties of liquids that you should know are vapor pressure, heat of vaporization, boiling point, viscosity, and surface tension. Then we talked about intermolecular forces, dipole-dipole attractions, instantaneous induced dipole attractions, and hydrogen bonds for unusually strong dipole attractions. Then we looked at this chart. This chart shows the most important are instantaneous induced dipole, right? These species. Well, actually, it isn't. Well, the most important appear to be what? Hydrogen bonds. Then, but when we get to heavier and heavier molecules, then the instantaneous induced dipoles are much more important. Okay. The polarization and that kind of stuff. So this chart is actually pretty difficult to understand. Then we talk about this. What was this? Now, this is
number of high energy.
Yeah, this is a population distribution. This is like if you have one of those, half marathons or something, or if you have a marathon. If you have a marathon, most of the people are running around here. You have a small group running way at the head and a group running at the end here, but the bulk are somewhere in the middle. Right? It's a population distribution. Now, if you give them some extra power, some extra energy, then, I don't know. So you give them some extra energy, it kicks the whole group up. So we looked at this. This is kind of what you want to do when you review. You kind of want to go through this and see, does this stuff make sense to me? If you can explain, a lot of people say this is probably a good task. If you can explain this to somebody else, then you probably have a pretty decent grasp of it. If you can't explain this to somebody else, then you need to get a better grasp. We should work on trying to explain. And so, can you explain this chart to somebody else?
Yeah.
Probably. A lot of people probably can. Even in Chem 1A, this is the this is the exact same chart in Chem 1A, and maybe about 90% of the students can't explain this chart in Chem 1A.
You explained it
which is the
yesterday.
next level. What's that? I explained it yesterday, but that doesn't mean anybody understood it.
Explain it again.
It makes sense.
Well, actually, this one I don't want to explain again because you don't have to worry too much about this.
It's the number of electrons.
You don't have to worry too much until you get to Chem 1A. When you get to Chem 1A, then you better understand this.
If you don't make it to Chem, you just die. You just can't handle it.
How about this?
Disregard that comment.
Oh yeah, that's the.
Can you explain this?
Yep, it's the liquid vapor equilibrium.
Yeah, this is the dynamic equilibrium.
Yeah.
Isn't that relative fluidity? It's like
Dynamic means change, equilibrium means no change. So explain that to me.
Dynamic.
just did.
So you change until there is no
Okay,
change.
yeah, there's no change. Once we hit this point, there's no change, but there is change. So
Change up.
once we hit here, it's plateaued, but there's change. What is the change?
Evaporation.
Evaporation never stops, and condensation never stops, but it's just churning. You know, it's not going anywhere. Yeah, it's really happening.
What the energy guys like stays within the system?
Yeah, it's just nothing. It appears that nothing's happening, but at the particulate level, when you look at the individual water molecules, they're cycling.
Until they run out of energy? Or they don't run out of energy?
They aren't going to run out of energy because they're at 25 degrees C, let's say. This is at 25 degrees C.
Also getting heat.
Yeah. Of course, it could run out of energy if you start taking away energy, cooling it down. These are the vapor pressure curves. The vapor pressure curves, this is also in Chem 1A. We don't do too much. The only thing we did was look at the boiling point. So, for example, can you boil water at room temperature? Did I show that video? Yeah, you can.
That's a better air pressure.
Okay, so those were the properties of liquids. Then we went on to solids. And so we had crystalline solids and amorphous solids. And whether it's crystalline or amorphous, we also classify it based on the types of bonds, you know, that we have. And so this would be amorphous solid. Amorphous solid is lacking long-range order, but this would also be held together by covalent bonds. Covalent solid. This is a crystalline solid here. This crystalline solid is held together by ionic bonds. This crystalline solid here, aluminum metal, is held together by metallic bonds. And silicon's held together by covalent bonds here. The types of bonds will dictate a lot of the properties. This one is fracturing on the bonds, breaking bonds. So it could fracture in a nice, clean, orderly way or a disordered way. Disordered would be amorphous, ordered here. But the types of bonds will have a big impact on the properties. What types of properties? Well, hardness, melting point, solubility. And so when we look at ionic solids, like KNO3, NaCl, MgO, you know, these are held together by strong ionic bonds. They're hard to melt. So they have high melting points. Generally, they're water soluble. You know, these salts, like KNO3, group 1. Group 1 salts are soluble. Nitrate salts are soluble. Sodium salts are soluble. MgO is actually insoluble. So magnesium oxide is insoluble. So that's why they say generally water soluble, but not all. They're brittle. They conduct only when melted or dissolved. In the solid state, they don't conduct. We have molecular solids like ice, you know, iodine, this C10H8. These are usually low melting because they're only held together by intermolecular attractions, such as dipole, instantaneous induced dipole, or London forces, and hydrogen bonds. The solubility depends if they're polar or non-polar. You know, if the solid is made up of non-polar molecules like iodine, then it likes non-polar solvents. If it's made up of polar, then it likes polar. So solubility depends. Then we have covalent, network covalent, like quartz and diamond. Quartz and diamond have very high melting points because it's hard to break covalent bonds. Network covalent. Network covalent would be like this. What they're talking about is having a network of covalent bonds. So this is quartz. You know what? Diamond looks just like this, except all the balls are carbon atoms. And it looked just like this. And so we have these covalent, polar covalent bonds here for quartz. Quartz is polar, but it's not very soluble because it's hard to break those covalent bonds. This is quartz here. That's network covalent. This is network ionic. Network ionic, we could have a network of ionic bonds in the lattice. These are held together by ionic bonds. Ionic bonds are strong. It's hard to melt this. So it's hard to melt this, and it's hard to melt this. But it's not so hard to melt this. This is a molecular solid. This is solid sulfur. Solid sulfur melts at about 100 degrees C. And it's easy to melt. It's easy to melt because the sulfur molecules, which form these 8 sulfur atom rings, are only held together by instantaneous induced dipoles. So these are only held together by these dipoles that are fleeting. They're here 1 second, they're gone the next. And so it's easy to break these molecules apart from each other. And so to melt this, we just break the S8 molecules apart from each other. This is another form of sulfur. This is called white sulfur, although it doesn't look so white, but it has a different structure. It forms these long, needle-like chains of sulfur atoms there. Is that amorphous? Yeah, that's amorphous. The yellow sulfur here on the left is crystalline, actually. And those are tiny crystals of sulfur.
The sulfurs, are they used in weaponry?
In what?
Like explosives?
Yeah, sulfur is some sulfur-containing compounds. Sulfur, you know, the violent reactions are the redox reactions. You have to really watch out for redox reactions. Metathesis reactions typically aren't nearly as violent, and acid-base reactions aren't nearly as violent. Redox reactions can potentially be very violent. Well, sulfur has some very interesting redox chemistry. Like, for example, H2S. H2S is, what's the oxidation state of sulfur run from what to what? Yeah, sulfur runs from +6 to -2. So it's got a wide range of oxidation. H2S has sulfur in the -2, so H2S is a good reducing agent. And sulfate has sulfur in the +6, so sulfate's a extreme. It's not extreme. Sulfate is not that powerful of an oxidizer, even though you think of +6 it should be powerful, but it isn't. Sulfate's pretty stable, surprisingly. It all depends, you know. Like, we always watch out for bleach, because bleach is a pretty good oxidizer, or bleach is a pretty good reducer. Oxidizer. Bleach is a pretty good oxidizer because chlorine is in the +1, but chlorine really likes to be in the -1. Like, -1 or even 0, you know, it's better than +1. And so you don't want to mix bleach with, well, I wanted to mix bleach with H2S because I wanted to oxidize the heck out of the H2S, you know. H2S smelled bad, it gave me headaches. And so if I could oxidize it to sulfate, then sulfate's not that bad. I mean, people eat sulfate. Sulfites, you know, people complain that sulfites give them headaches, you know. That's why a lot of wines say no sulfites in there. What do they use sulfate for? Sulfate is, well, what do they use? Sulfate, has different uses, but it's not, probably the biggest use of sulfate, you know what the biggest use of sulfate is? Sulfuric acid is the biggest use. But if you want to see the major industrial uses of different agents, there are a whole bunch of lists. So we could just go to Wikipedia. Let's look at commercial applications. Well, it's not really. Calcium sulfate is a common chemical. Copper sulfate's used to kill algae. Iron 2 sulfate. We use iron 2 sulfate for testing for nitrate, and you're going to use iron 2 sulfate tomorrow in lab to test for nitrate. You know, it's the green solution. But people use it for supplements because, you know, the iron in hemoglobin, is it iron 2 or iron 3 in hemoglobin? Iron 2. So the iron in your blood is iron 2. Iron 2 sulfate, a common form of iron in mineral supplements for humans, animals, and soils and plants. But it's easily oxidized. Iron 2 gets oxidized to iron 3. Magnesium sulfate is called Epsom salts, and people make Epsom salt baths for their feet. Lead 2 sulfate is used in car batteries. Sodium lauryl sulfate is detergent in shampoos. Polyhalite, which is potassium, calcium, magnesium sulfate, is fertilizer, etc. So there are different uses for sulfates. There are things that that use sulfate, like anaerobic bacteria. These anaerobic bacteria eat the sulfate basically and convert the sulfate into H2S, and so it starts to stink like rotten eggs around these bacteria. And so yeah, in hot springs, exactly. In hot springs, you notice the H2S smell. That's from the bacteria, these anaerobic bacteria.
And it's toxic?
H2S is toxic. H2S, somebody died not so long ago. When was it? In Ventura. H2S death, Ventura. Yeah, unfortunately. Yeah, actually not somebody, 3 people died. Sorry. 3 people were killed in Ventura. 4 injured. They're overcome by H2S fumes. This happened at the one of the oil places in Rincon, Seacliff. Oil field. You know, the 101 goes right by there. Some places you can really smell it. Have you been to Trona, California? Trona, California. No, in Trona, it's on the way to Death Valley. And so you drive up through Trona, and you want to leave your windows up, because if you put your windows down, you're just going to get overwhelmed by H2S fumes. The place just reeks of H2S. So if you want to smell H2S, go to Trona. You know, stay at the motel there in Trona. You're going to have plenty of H2S. Yeah, there's a story about Trona, though. The town is dying. Not from the H2S, but from the loss of jobs. The loss of jobs, the mining jobs in Trona. But the townsfolk, they don't mind H2S, they're used to it. But the problem with H2S is it's very deadly. H2S fatigues your sense of smell. So initially you smell it, and then you don't smell it anymore because your olfactory sensors have been saturated with H2S and they can't detect it anymore.
Why is that so bad?
And then it only takes part per billion levels to kill you. So this is why. All right, the last part of chapter 15 deals with changes. So if we start off with a solid, and then we heat it, what's going to happen eventually? It's going to melt into a liquid. So this will be melting. What if we take a liquid and cool it? It'll be a solid, right? And so melting a solid is called melting, but it also has another name. You know another name for melting? And this is a weird name. I could never figure out why they call it fusion. Because usually when I think of fusion, I don't think of melting, but fusion is another name for melting. This is not nuclear fusion. Nuclear fusion is different. And then if we freeze it, what's it called? It's called freezing or solidification. We'll just call it freezing. If I take a liquid and heat it, do you know what it's going to happen? It's going to turn into gas, and we call that process or boiling. Evaporation or boiling. Or one more. You know one more? Not evaporation, not boiling, but vaporization. Vaporization. And what's the reverse called? Condensation. We'll just call it condensation. Okay, these are called phase changes. We're changing phase, solid to liquid to gas. Those are phase changes.
What about solid to gas?
Solid to gas? Well, sublimation is the,
Isn't it start with a D?
yeah. Sublimation is it. Sublimation is going from a solid directly to the gas. So dry ice sublimes. It doesn't melt and it doesn't boil under normal conditions.
I was right, that position was.
Yeah. And the reverse process of this is called
Deposition.
deposition. It starts with a D.
That was so good.
That was good. That's good memory.
Thank you. Can I get a point for that? I want to get points all the freaking time. He gets points for like D and
Yeah, just keep doing it. Keep getting the right answers and get the point.
That's really hard and you know it. It's not easy.
All right. What we're going to do is we're going to do some calculations now. The calculations that we're going to do are this. We're going to look at the energy. You know, how much heat is involved? Heat. You know, how much heat do we have to add, or how much do we have to remove? You know, when we cool it. Cooling is just removing energy. Heating is adding energy. And so heat, Q, is the energy. And so if we add heat, then the Q is greater than 0. It's positive. If we remove heat, then Q is less than 0. It's negative. And so we can figure out how much heat we have to add or remove to do certain things. So for example, heat of fusion. Heat of fusion, what do you think that relates to? Heat required to melt. And so for phase changes, we're going to use this equation. The amount of energy, Q, is going to be related to how much, which is the amount. And the amount is usually in grams, times delta H of the phase change. And so what are our delta H's of phase change? Well, we have fusion here. And so if we want to melt ice, it's going to cost us 333 joules per gram. We also have the heat of vaporization. If we want to boil water, it's going to cost us 2.26 kilojoules per gram. But what about freezing and condensation? And so delta H of freezing is equal and opposite delta H of fusion. So if it costs a certain amount to melt, then we're going to get that amount back when we freeze it. So if let's say it costs $10 to melt, then we're going to get $10 back when it's frozen. Delta H of condensation is equal and opposite of delta H of vaporization. And delta H is called the enthalpy change. H is the enthalpy, so it's the enthalpy related to these processes. Right? And using this equation and these numbers, we can do calculations to figure out how much heat is required to melt a certain amount of ice or boil a certain amount of water. And so we have these. If you look at the delta H of fusion, which of these requires the most energy to melt? Looks like. Well, water costs us 333. Sodium chloride. Sodium chloride is going to cost a lot of energy to melt. Because it's hard to boil. But you know, if it's hard to melt, then the temperature is going to be high, the melting temperature. And so the melting point of sodium chloride is 801 degrees C, or over 1,000 degrees Fahrenheit.
So it's not even the one that.
I know, it's not the highest heat.
Yeah, the highest one is iron.
Is
Iron?
it because it's denser?
Iron, oh, the temperature? Yeah, it's not exactly correlated. You're right. It's a little odd. It has to do with multiple factors. That's fine. What factors? Like the bonding in there, and how it absorbs the heat. You know, how it absorbs energy. So if you look, it doesn't exactly correlate like water. If you look at water, water is very high, 333, but its melting point's only 0 degrees C. That's because water has lots of different ways it can absorb that energy. When water absorbs energy, you can cause rotations, you can cause vibrations, and you can cause translations. When iron absorbs the energy, you can only cause vibrations. And so there are a lot more modes of energy absorption for water than there are for iron. And so it creates a difference in how the energy. Those modes are actually quantized, and so you can, you know, there's certain energies that are allowed and certain energies that are forbidden for absorption of these things from quantum mechanics. But anyway, let's take a look at this. How much energy is needed to vaporize 188 grams of a liquid if its heat of vaporization is 1.13 kilojoules per gram? And so this is a pretty straightforward dimensional analysis. If it takes 1 kilojoule per gram to memorize, to vaporize, and we have 180 grams, so it's going to be 180 times that. We can set this up as a dimensional analysis problem. And that is 188 grams. Let's see if we get the light up there. And then we use this as a conversion factor. Grams cancel, left with kilojoules. So that's it. Or we can use this equation. Q is equal to amount times delta H. This is going to be delta H of vaporization because we're boiling it. Or vaporizing it. And so it comes out to 212 kilojoules. How much energy is required to melt 25 grams of ice at 0 degrees C? So it's the same thing here. 25 grams, 25.0 grams, and it costs us 333 joules per gram. So 333 times 25. That gives us 8.33 times 10 to the third joules, or 8.33 kilojoules. Okay, that is for phase changes. But let's say this. Let's say I have water, H2O liquid, at 50 degrees C. If I add heat to this, will it start boiling right away? No. If I add heat to this, I'm going to have to wait until it warms up all the way to, what temperature does water boil at? At 100 degrees C. And so if I want to boil the water, it doesn't boil at 50, it boils at 100. And so what I have to do is I have to warm the water first. And so if I'm warming or cooling, then that's different than a phase change. So I could be in between phase changes. I can be in a single phase. This is a single phase liquid to liquid phase. And so this is called warming and cooling. When I boil water, does it boil at 100 or does it boil above 100 or below 100?
At 100.
At 100 under normal conditions. You know, it boils at 100. Does the temperature change? If you have a pot of boiling water, is it getting hotter and hotter and hotter, or is the temperature pretty much steady?
Steady.
It's steady, it's constant. And so when we're doing a phase change, there's no temperature there because the temperature is whatever. If it's boiling, we're at the boiling point. If it's melting, we're at the melting point. But if we're not at the boiling point or the melting point, then when we add heat, it's either going to warm, or when we remove heat, it's going to cool. And we use a different equation for that. Q is equal to the amount times C times delta T. The amount is usually in grams, so we'll call it mass, little m. C times delta T. Delta T is the temperature change. C is called the specific heat. And the specific heats we look up in a table. And so let's take a look at the table of specific heats here and take a look at what do you see has the highest specific heat. So when we look at the specific heats, the highest is liquid water, 4.18. The units are joules per gram degree C. What has the lowest specific heat? Gold or lead? You know, I don't know which one's lower because it's only 2 sig, so it looks the same, but they are. One is gold solid, the other is gold liquid, molten gold. Well, anyway, what that means is the specific heat means this. The specific heat relates heat with amount and temperature. And so something with a high specific heat means you have to add a lot of heat to raise the temperature. Something with a low specific heat means you don't need much heat to raise the temperature. So gold warms up rapidly. Does water warm up rapidly? No, water takes a long time to warm up. So we're out of time, so we'll continue this next time.